Okay, the next speaker is Henry Lin, and he'll tell us about bootstrapping D0 quantum mechanics.
Okay, thanks for the invitation. Yeah, this talk is based on two papers, one of which is upcoming, both with my collaborator Zechwan. And it's also, there are many other relevant works, which I'll try to review. So I'll start with a trivial statement, which is that it would be nice to solve large N-gauge theories, even in the strict 't Hooft limit. Now, today we're going to take a very tiny step in that direction, and we're going to try to find a bootstrap solution of one of the simplest large N-gauge theories, which is the so-called D0 brane quantum mechanics. So this is the reduction of 10D n equals 1 super Yang mills, or 4D n equals 4 super Yang mills down to 0 plus 1 dimensions. Okay, so we won't have any of the complexities of the lattice and renormalization, etc. It has an interesting gravity dual, which I will not review, but it's a very interesting dual. And our goal is to compute in the large N limit some very simple quantities. So we're interested in the vacuum state, so this is omega, and we're interested in, say, single trace observables in the vacuum state. Okay, so this is supposed to be hard, and it's hard analytically because the super Yang mills interaction in D less than 4 is relevant, right? So if we're interested in the ground state, this is some very strongly coupled problem. And it's also hard numerically. So numerically, there have been some really fantastic Monte Carlo simulations of this model. But these Monte Carlo simulations are sort of non-trivial, both in terms of computational resources and also due to some subtle conceptual points. Okay, so the first point is just that for Monte Carlo, physics is somehow simplifying at large N, right? But the Monte Carlo simulation is getting harder, so that's slightly awkward. A more serious problem is that there's a sign problem. So in this theory and many other gauge theories, as we've heard, we have sign problems because of fermions or potentially theta angles or whatever. In this model, we would expect generically that there should be a sign problem in this model because of the fermions. And there's also some issues of metastability. So there's a class of problems, including the BFSS model at finite temperature, which are strictly speaking not totally well defined at finite n. Okay, so they're well defined at infinite n, but at finite n, they're not perfectly well defined. And physically, in the BFSS model at finite temperature, it's related to the fact that you have a black hole that can Hawking evaporate. So it doesn't really make sense to isolate the black hole at finite n. Okay, we'll return to this point a little later. Okay, so in contrast, there's this other method, which sometimes is called large N bootstrap. And it's nice because it works directly at infinite n. It gives rigorous bounds. There's no sign problem. But there's some disadvantages. So one disadvantage is, in a Monte Carlo simulation, if you want to double the number of matrices, you don't really pay a huge overhead. But for the bootstrap, naively, the difference between one matrix and two matrix is huge, right? So you suddenly have a proliferation of correlation functions. There's this sort of Hagedorn growth of the number of correlators, right? And you also have not just exponentially many observables, but also a large number of equations of motion and positivity constraints. Okay, so the BFSS model has many matrices. So to deal with this in some systematic way, we'll have to use some group theory or some other method to avoid this problem. Okay, but just one more slide of motivation. So just to show you that the method actually can work for models which are not integrable. So Kazakov and Zhang in 2022 bootstrapped this two-matrix integral with a commutator squared interaction. And this model is not believed to be solvable. And they got 6 digits of precision for some simple correlators. Okay, so and they did this on a laptop, and they said that it was many orders of magnitude faster than Monte Carlo if you want to get the same number of digits. Okay, so that's some motivation to try to attack the BFSS problem. Okay, and I won't go through the history of this method. The only thing I want to highlight is that it has some sort of interesting out-of-time order contour. And in particular, Polchinski in 1999 gave an argument about BFSS that today I will try to argue is part of the bootstrap philosophy. So you might think that that's just some propaganda, but I'll try to convince you that it's not propaganda, or at least good propaganda. Okay, so now we have the BFSS model. Here's the Hamiltonian. It has n equals 16 SUSY. So here are the supercharges, right? These operators satisfy the same algebra that we heard about before. The fermions, of course, are also, they're 16 fermions because they transform in the spinor of SO9, okay? And here C is the gauge constraint. So we're going to be interested in the ground state. So whether or not you think the model is gauged or ungaged, you can always impose the gauge constraint for the ground state. Okay, so there are two ingredients in any bootstrap. First, the constraints, which I will now explain. So the constraints are very similar to what you heard about before lunch. So the only difference is we're going to use the supercharge equations of motion instead of the Hamiltonian equations of motion. Okay, so we use the fact that the supercharge annihilates the state in the vacuum state. And what we do is, to use that constraint, we simply list all possible SO9 spinor operators, O alpha. Okay. In order for this equation to be non-trivial, in a state which is an SO9 singlet, O alpha has to be a spinor, right? So as an example, you could choose this operator, and well, if you apply the supercharge, for example, you get a commutator term from the interaction, right? And so in general, you'll get some relations between correlation functions. So it's very similar to the Hamiltonian equations motion that we heard about earlier. Now, to organize of course, in principle, we should list all possible operators, but in practice, we want to organize this in some practical way, right? So we're going to introduce some sort of hierarchy. So the correlators that we're interested in are traces of words, and the words are composed of letters. So the three possible letters are X, psi, and P, and we're going to assign levels to each word, to each character. So X has level 1, psi has level 3/2, and P has level 2. This is basically the scaling dimension of the operator in the UV theory. And this definition is nice because when we act with the supercharge on a given operator, it always increases the level of the operator by 1/2. Okay, so by using this hierarchy, we can build out, we can find all constraints that this supercharge will generate up to a certain level. And then we have the kinematic constraints. So we have SO9 invariance, we have SUN invariance, and we also have the cyclicity of the trace. So cyclicity of the trace, just to give you another example that's different from Josh's, if you have a trace of x's and p's, let's say you push this last x through the trace to use cyclicity, you'll get this term, right? But you'll also get some other term that comes from the fact that there's a commutation relation between x and p, right? So in fact, that term actually generates a double trace because whenever it hits here, the indices will be contracted in these respective ways, right? So actually, this is the only place that we use large N. So we use the cyclicity relations. That generates relations that involve double traces, and we factorize the double traces. So that's how infinite N is input. And then we have to do some, so the last, I glossed over the SO9 invariance. That sounds trivial, but it's actually the hardest part of this project. Okay, so the constraint is, of course, just that SO9 invariant operators have non-zero BEVs, and those are the only operators. But we can't simply enumerate SO9 invariants because positivity requires that we consider non-singlets in intermediate steps. Okay, so to take a trivial example, we know that trace of x squared is positive, right? But how do you know that? You know that because it's the sum of squares, right? But each term xj is in the vector representation, right? So this is just a trivial example to show you that you need to consider the vector representation in order to prove that the singlet is positive. Okay, so a slightly less trivial example is this object. So you can think of this as a positivity matrix in the combined indices delta eta and alpha beta, right? So this is some operator and this is its conjugate. So we would like to impose that this matrix is positive semi-definite. And the idea is we can first enumerate all possible singlet structures that appear on the right-hand side. Okay, so basically you contract these alpha and betas into whatever they can be. And you know from group theory that they're basically the two spinors gives you the antisymmetric tensors. So those are the 5 antisymmetric tensors. And then the fact that you have an antisymmetric tensor, this one also gives you an antisymmetric tensor. So you end up getting 5 non-singlets. 5 singlets in this expansion. Right? So there are 5 possible terms on the right-hand side parameterized by these A's. And that's the final answer for what this matrix could be in an SO9 invariant state, right? So we've reduced a very big matrix, right, with a lot of elements into just a matrix parameterized by 5 elements. So that's good. That's step one. But there's actually a little bit more. So what I said in pictures, remember we decomposed alpha and beta into some era, and then we also decomposed the other 2 fermions into some era, right? You could also decompose it in a different way. And in fact, cyclicity requires that you decompose it in a different way. So in general, we will encounter both the S channel and the T channel, and we will need the crossing kernel to relate these 2 decompositions. So in this very simple example of fermions, you actually know what this is. This is just the Fiers identities that you learn about in QFT. But more generally, if I put some more general irreps, you need the so-called 6J symbol in order to solve this equation. So most of our time was spent developing some algorithm for computing these 6J symbols. Now, okay, so at the end of the day, you impose cyclicity, you cut down these 5 unknowns to just 2 unknowns. And if you think about, in analogy with the conformal bootstrap, right, the terms that appear here would be like the OP coefficient squared, right? So these are the things that are positive. So at the end of the day, you've reduced a huge positivity matrix to just the positivity of a few numbers. And those are what you actually impose. Okay, so if you didn't follow the details, the main upshot is that we do some group theory, and that makes the bootstrap a little bit more practical. Now, here I just give you some sense of the numbers. So at different levels, we of course have more variables. So these are the SO9 singlets. And then once we quotient by all of the, let's say, equations of motion and kinematic constraints, we of course have fewer variables. And you can see that there's actually not that many free variables, even at level 9. So even at level 9, this is considered a very small STP problem by bootstrap standards.
So this used fermions, or it could be boson?
Yes, both fermions, and all SO9. We were very careful to enumerate all possible SO9 irreps. Yeah. So let me just show you some results. So here is our sort of best constraint at level 9. Okay. I'm plotting on the axis 3 different correlation functions. So on this axis is trace x squared. On a different axis is the kinetic term, so trace p squared. You could equivalently think of that as trace of the commutator squared, because in the ground state they're the same. And then we have some purely fermionic operator. So this is a 4 fermion operator. And the allowed region is this boot. Right? It doesn't really look like a boot, but we're calling it boot for obvious reason. So the allowed region is the thing inside of here. And there's also a nice kink. So you can actually argue by some analytic arguments that this is a true kink. It's not round at that point. So according to bootstrap lore, there must be something interesting near the kink. And if we clean up the picture a little bit, we can plot, let's say, the kinetic term against just trace x squared. And we can also use the Monte Carlo results. There's 2 separate Monte Carlo results. They both give roughly the same answer, and they're both pretty close to the tip of the peninsula. Okay. Yeah, just to give you a sense, at level 9, to generate any point on this plot takes only a few seconds. So this is a relatively small STP problem. The only reason we didn't go higher is due to some issues with the group theory, which I could discuss if you're interested. A different way to look at this plot is the following. So let's consider a different operator, trace x squared, and then we see some sort of interesting pattern. So the question is, what happens as we try to approach the tip of this peninsula? Okay, so we're imagining going from trace x squared large up to the tip of the peninsula, and we're tracking what happens to a different observable trace x squared. Okay, that's roughly like trace x to the 4th, but I've written it that way to indicate the particular Wick contraction that's relevant. Okay, so what happens is kind of interesting. So if you look at high levels, what ends up happening is as you approach the tip of the peninsula, this other variable, trace x squared, shoots up to infinity. So in order to actually land on that tip, you would need a different observable to sort of diverge. Okay? So we actually think that the true value of trace x squared is not quite the tip, which would be sort of the tangent line of this, but it's actually sort of a corner. It's probably somewhere around here. So that's a speculation. But the main point is that already at level 9, these kind of tips seem to be converging somewhat. I mean, it's not perfect evidence, but if you look at the tip of the peninsula here and here, they seem to be converging, and here are the actual numbers if you're interested in. I should also mention that the Monte Carlo result is a little bit subtle. So if you look at this bootstrap bound, you could claim that we rule out, let's say, part of the error bar in the Monte Carlo experiment already. To say that a little bit better is somewhat subtle because, so for example, if you look at how they actually do the calculation in the Monte Carlo, so they're calculating trace x squared, that's this blue curve, this is r squared. So they do it at various mass parameters. So they put this theory in a box to cure the metastability issue, roughly, so that they turn on some mass terms. And as a function of mass, they have a slightly funny behavior, right? So as the mass decreases, the trace x squared actually grows slightly. And then they say that the true value is here. So when I say that the error bar on the previous slide, it's roughly this error bar here. So the fact that the value of trace x squared grows as mass decreases is some sign of metastability. Okay, so yeah, I presented some evidence that the bootstrap could yield precision data on some correlators, like trace x squared, for example. Maybe just one more comment, which is that even at level 7 or something, if you want these results, which are sort of approaching the edge of the uncertainty, you really need extremely tiny SDP problems. So once you do all this group theory, you only have like 20 by 20 matrices, and you can do that in like 1 second on the computer. I'm trying to present to you some evidence that the bootstrap could eventually yield precision data on some correlators like trace x squared. Now, you might ask me, why do we care about these kind of correlators? Well, in principle, I think it shows that you can compute some interesting, strongly coupled physics. Like, these are some constraints on the ground state wave function of the theory. But of course, another motivation is that perhaps we'd like to learn something about gravity. So because this model has an interesting gravity dual, we could hope to learn some new things about string theory in this particular background. So let's say in the 't Hooft limit, which is the limit which is relevant for doing the large N bootstrap, this model is dual to some sort of semi-classical black hole in type 2a. Okay? And in fact, the leading corrections to this black hole metric are not known. And that's because you need the full alpha prime cubed correction to the 2a effective action. And that is unfortunately not known. So these points were already made in the Monte Carlo papers. And I'm just repeating them here. I think a good candidate in the future for doing a bootstrap study would be to study a particular operator, which is a BPS operator that is SO9 singlet, and study it as a function of temperature or energy. And then there's a concrete prediction from the gravity solution for what its behavior should be. So besides the thermodynamics, there are some predictions for these correlation functions. In principle, if you could compute these to very high precision, you can read off some properties of the alpha prime cubed effective action that are currently unknown by worldsheet methods. Okay, I think I'll make one more comment. So the fact that these two results agree, so the bootstrap results and the Monte Carlo results sort of agree, suggests that the sign problem is not actually a problem. And that was already argued for in some earlier work by the Monte Carlo people. And with some, this is some work in progress, but we're interested in trying to analyze this a little bit better. So the idea is that when people do Monte Carlo, they integrate out the fermions and they get some determinant. And instead of using that as the measure, they put an absolute value on it, right? And naively, that seems like a bad idea, but they tried doing this with and without the absolute value for some relatively low, for temperatures of order 1 and for relatively modest values of n, and they didn't see a huge difference. So they tried to argue that this is a good procedure. I'm actually a little bit surprised that this Monte Carlo result so far is consistent with Bootstrap. So one way of testing whether there's an actual sign problem is just to keep doing the Bootstrap and seeing if we eventually exclude this point or not. But a different way would be to try to understand it a bit analytically. And in particular, you could write the Pfaffian. You could think of the absolute value as a replica limit, right? So you first calculate the Pfaffian to the 2n, and then take n goes to 1/2. And the reason why I'm writing it this way is because the Pfaffian to the 2n can be represented in terms of just increasing the number of fermions, right? So by studying this theory with more fermions, you can, and doing perturbation theory at high temperature, you can test whether or not there's actually a sign problem. So far we did the calculation up to one loop at in the high temperature expansion. So recall that the model has a relevant coupling. So at high temperatures, it's weakly coupled. So we can do some sort of perturbative calculation at high temperatures. And up to one loop, we see no evidence of a sign problem. So at tree level, this is totally trivial because there's no fermions at high temperature. But at one loop, you get some non-trivial matrix integral, and you just find that for any value of n, these two theories are equivalent. Okay. So yeah, to say it a little bit more carefully, you find that this theory with both A and A star is equivalent to a theory with just two n's with just A. And that you find for any value of n. So that shows that at one loop there is no sign problem. But at higher loops, we expect that there should be a sign problem. Of course, if you believe this bootstrap result and you believe the Monte Carlo result, then you might think that there shouldn't be a sign problem. And we should be able to see this by looking at higher loops. Okay, so to give a few more future directions, first question that you're probably going to ask me if I don't ask it to myself is whether or not we actually get islands in any situation. So up to the current level, we do not get islands yet. But I want to make a small comment about that. So if you look at a different model, so this is called the toy supermembrane model. It's just a model which is Hamiltonian quantum mechanics with two coordinates, x and y. The Hamiltonian is px squared plus py squared. Plus x squared, y squared. Okay, so this is a somewhat famous toy model of the D0 brane theory, and it shares the feature that classically there are some flat directions, right? So classically there are some flat directions, but quantum mechanically there's a bound state. And you could ask whether the bootstrap actually finds the bound state or whether it doesn't find the bound state. And what you see is at low level, you get a plot of, so here I'm plotting the energy, which is roughly analogous to the kinetic energy that I was plotting in the previous talk, in the previous slide. And here I'm plotting it against x squared, which is obviously analogous to trace x squared. And you see a very similar looking shape, but eventually when you go to high levels, you find a little island that's not too far from the tip of the peninsula. Okay, so in this very simple model, this would be like a dream scenario for what happens at higher levels in the bootstrap. Another point that I was going to make since I have the time is this gray curve. This gray curve that I showed earlier. So recall what this was. This was trace x squared versus trace x squared. The gray curve is the lowest level constraints at level 4. This was actually.
Grab your microphone.
Oh. Yeah. Yeah, this gray curve was actually already produced by Polchinski in 1999. Okay, so actually his curve was basically a dotted line here that says that everything above that dotted line is allowed. And a very minor improvement would actually give you this gray curve. So I'll give him, I'll call this the Polchinski curve. And the interesting thing is that notice that the Polchinski curve in gray does not give any lower bound even on trace x squared. So it's only bounded by 0 for trace x squared. It does give a lower bound on trace x to the 4th, basically, but not trace x squared. And that's just how it is. You need to include, if you just add just a little bit of fermionic information. So this is level 5. At level 5, recall that level 5 is 2.5 plus 2.5. So the irreps are 2.5, right, that appear in the matrix, and therefore they're fermionic. So that just means adding the first fermionic operator already gives you a lower bound on trace x squared. So that's just something kind of interesting. So we're hoping that going beyond level 9 will be similar to this plot that I showed. And one evidence of this is, so at level 9, you involve the epsilon tensor for the first time in a non-trivial way. And at higher levels, you really make use of sort of many special facts about SO9. So maybe, I mean, this is just some vague comment that maybe the constraints are more powerful enough to actually pin down the bound state in this model. Other future directions, we could do finite energy, finite temperature futuristically. So that was, of course, already discussed in Josh's talk. We would like to eventually do other large N lattice systems, especially those with sign problems. So I think this community has provided some inspiration for those directions. And then, of course, we could discuss other quantum mechanical matrix models, BMN. Perhaps in the future we could imagine doing something with IKKT, although there are many questions. Okay, so thanks a lot. I think I destroyed this microphone.
Jan?
Oh.
I think out of the matrix models, the one with 16 supercharge and 8 supercharge has sign problems because of the cover. But the one which is the reduction of n equals 1 super Young Mills to d equals 0 dimension, that matrix model does not have a sign problem.
I see.
And the IKKT one is a sign. There is a paper by this is essentially zero mode of BFSS.
Yes, yes, with
And
periodic
there's a
boundary
paper
conditions.
by, with periodic boundary. There's a paper by, maybe probably by Plevka and others. And they show explicitly how the zero mode arise by doing computation. But in the past, I did similar computation for Witte Kaplan for matrix model with 4 supercharge. In that case, there is no sign problem.
Okay, thanks a lot. Yeah, I guess that would be a good thing for us. So when we do this computation, we leave it fairly general. So
Yeah.
we should check that
Yeah.
indeed for.
Other questions?
So is there a way to systematically do one-over-n corrections in this framework?
No, not that's known. It's been discussed by some people, some speculative. Yeah. The main difficulty is that, you see, the difficulty is that at large n you need to saturate some sort of positivity inequalities in order for the 1/n corrections to have interesting positivity constraints. Another comment I can make is the question of 1/n, or for example, if you're interested in the time-dependent correlator, which is down by 1/n, right? Yeah, naively you would have the same problem. It has been discussed how to bootstrap off-diagonal matrix elements of operators. So instead of just having the vacuum, you could put vacuum on one side and energy on the other side. That can be accessed through the bootstrap. And so indirectly, that tells you about the time dependence of the correlator. But it's not as satisfactory as a direct 1/n method.
Yeah.
So in the toy model plot to any island, do you need to impose extra constraints or do you just increase the?
Yeah, just increasing the level. Yeah.
So you hope the same thing will happen?
I hope the same thing will happen, yes. There's another subtlety, which is at finite n, there actually are divergent operators in the BFSS model. So like trace of x to some high power is expected to diverge because there's some power law tails in the bound state wave function. So that would also be interesting to see in the bootstrap. So if you did it at finite n, you would presumably see that you have some lower bound that just keeps receding as you increase the constraints. Yeah, we were actually wondering whether there's any quantum mechanical model which has the same features of having basically a threshold bound, a marginally bound state with the power law tails, but we couldn't find. So this x squared y squared model is not sophisticated enough to have those features.
How about the supersymmetric version of the x squared y
Yeah.
squared?
Yeah, we were.
That would cancel the increase of the energy of the ground state.
Indeed. We're hoping to do that next. We actually did not do that yet, but that's a good toy model.
I think so.
All right, let's thank Henry again.
We don't leave yet. We figured this would be a good time to thank everyone, and especially to thank Charlene for all the great work she did on this workshop. It was a kind of two-step workshop, and correlating everything and making all the arrangements here. And we see that the room is still full, which is
That's good.
a sign of success. So just
Don't
a
leave.
small token of our appreciation.